To lesson 10.2.2. Starts off with kind of a weird problem. It's pretty cool though. Kind of a shout out to how smart this guy was, Eratosthenes. No idea how to say his name. Anyway, but it does end up with some very important things that we're going to need to know in terms of some angle and arc relationships. So make sure that you pick those up. So, to learn more about circles, you need to investigate different types of angles and arcs that are found in circles. In lesson 10.2.1, you studied an application with a piece of tree to learn about the arcs of a circle. Today, you will study a different application that will demonstrate the importance of knowing how to measure the angles and arcs within a circle. So, Eratosthenes, we're going to call him E. E's remarkable discovery. E, who lived in 3rd century BC, was able to determine the circumference of Earth at a time when most people thought the world was flat. Since he was convinced the Earth was round, he realized that he could use the shadow to help calculate Earth's radius. E knew that the town of Alexandria was located about 500 miles north of a town that was closer to the equator called Syene. So these two towns are about 500 miles apart. When the sun was directly overhead at Syene, a meter stick had no shadow. So he's got a meter stick standing up here and a meter stick standing up here. And you can see what's going on is the sun's rays are coming in parallel. That's important. Parallel. And there's no shadow here, but there is a shadow here. So he was able to kind of determine, well, that wouldn't make sense if the Earth was flat. They would both have no shadows. So he set about doing some math to kind of prove like how big Earth was, which is kind of crazy if you think about it. So pretty brilliant what he did. So here's what he did. However, at the same time in Alexandria, a meter stick had a shadow due to the Earth's curvature. Since the sun is so far away from Earth, E assumed that the sun's rays were essentially parallel once they entered the Earth's atmosphere, and thus he could use the stick's shadow to calculate the Earth's radius. Unfortunately, the precise data used by E was lost long ago. However, if E used a meter stick for his experiment today, then the stick's shadow in Alexandria would be 127 millimeters long. Determine the angle theta. Obviously, we've dealt with theta before. We've done with trig before, so we're going to need that. So hopefully you guys recall that. That the sun's rays make when the meter stick. Remember that the meter stick is 1,000 millimeters long. So if we look here, kind of important, we're using this triangle right here. So we have, good Lord, my inability to draw with this is really getting old. All right, so this is going to be 1,000 millimeters long. The shadow is going to be 127 millimeters long. You can see I'm sort of using that there, using this triangle that we have right here. And he wants to know what theta is. So I kind of need to rotate this up a little bit to kind of match this triangle. But he wants to know what theta is. So using trig, we can say it's opposite over hypotenuse. I'm sorry, opposite over adjacent, which is tangent. So we want to know what the tangent of theta is if it's equal to 127 over 1,000. So we're going to get this angle right here. We'll go to this trig calculator. I will make sure that I'm in degree mode, which I now am. And I want to know the arctangent. Again, I want to know what the angle is, so I'm going to go arctangent. What's the arctangent of 127 divided by 1,000? And it's going to tell me it's 7.24 degrees. So theta is going to equal 7.24 degrees. So that's the angle of theta. So if we go to, actually I guess I should put here, theta is that's about 7.24 degrees. Now it's asking us, assuming the sun's rays are essentially parallel, determine the central angle of the circle. Well, here's the central angle. Well, it's saying that these sun's rays are parallel. Here's our transversal. We know that this part right here is 7.24. Well, these are alternate interior angles. So because of alternate interior angles, I can say that my central angle is also 7.24 degrees. And again, just to point out We got trig in this problem. We have alternate interior angles, which goes way back to chapter 1. Chapter 3 is trig. Chapter 3 is in 4 was trig. So there's a bunch of stuff going on that we need to remember from the olden days. If we didn't learn that stuff, we really are kind of in trouble moving forward. Not only for integrated 2, but for integrated 3 as well. So just keep that in mind. So since the distance along Earth's surface from Alexandria is 500 miles, that is the same as the length of the arc between Alexandria and Syene, whatever. Use this information to approximate the circumference of Earth. So what they're telling us is this. We have the central angle of 7.24 degrees and an intercepted arc of 500 miles. So how much is the whole thing? Well, I know that it's going to be 2 pi r. 2 pi r. I don't know what the radius is, so it's actually, we want to get the circumference of the Earth first. So, yeah, I mean, I guess if we look at this, so we have 2 pi r is going to equal 7.24 out of 360 degrees, right? And we know that that's going to equal 500 miles. So we can kind of work backwards to get the radius here. I guess I'm going to do D first, and I'll come back and do C in a second. It just makes more sense to my brain to figure out what the radius is first, and then to figure out what the total circumference is second. So I know that the circumference is 2 pi r, and I know, but I don't have the radius, so I will figure out 2 pi r is going to be the entire circumference of the entire Earth, and I know that this little sliver of it equals 500. So what I'll do is I will multiply 2 times pi times r. I'll just leave that. I know I have an r there. That's what this is all going to equal. Times 7.24 divided by 500. That's going to equal 0.9090. Radius equals 500. So I'll divide 500 by that. By the answer. That 0.9090 thing. And I'm going to get the wrong answer. So let's go back here. I'm not sure if I punched something incorrect in the calculator. I feel pretty confident about my setup, so I'm going to try this one more time. I get 2 pi times 7.24 divided by 360 is equal to 0.12. See, I think I did something wrong. I had the right thing here, but I had the wrong answer here. So I think I am on the right track this time. So 0.1263. I guess if you go back and look, you can see what it was I screwed up when I punched that in. I had the right formula written down here. I just punched it in incorrectly. So when I divide this, I'm going to get a radius of, again, I'll divide this 500 by my radius, which is my answer. So I'll just go second answer. And I get 3,957 is going to be my radius. 3,957 is my radius, miles. Now I can work backwards and just go 2 pi r, right, to get what the circumference of the Earth is. So I'll go back here and I will say 2 times pi times my radius of 3,957, and I will get a circumference of 24,862 miles. Again, I guess it would have been easier to get the circumference first and then get the radius second, but for some reason my brain jumped straight to figuring out the radius first using this, and then using the radius to go and get the circumference, which is of course 2 pi r. So I hope you guys follow that. So, long story short, none of this is really even that important to what we're doing today, but I think it is worth a nod to kind of look at what these dudes were doing in 300 BC? 3rd century BC. That's a big deal that people were doing this kind of a math. I never would have figured this out on my own, although I'm not the smartest person, but that's pretty impressive that this guy was able to figure all this stuff out. All right, so let's go ahead and keep moving along. And I want to close this here. This video is obviously going to be longer than I would like. So, and again, there is a payoff at the end that you absolutely have to know. So hopefully you guys stick with the video long enough to get to the payoff. So, parts of a circle, part 2. To determine the circumference of Earth, E used an angle that had its vertex at the center of the circle. Like the angles and polygons you studied in chapter 8, this is called the central angle. So we're already familiar with the central angle. An arc is a connected part of a circle. So obviously this is the arc. So we should know what a central angle is. We should know what an arc is from previous chapters. For example, circle T, by the way, this is how you say circle T. Circle T, you name it circle with the center of it. So at right, angle STU is the central angle, and it corresponds to this arc of SU. Since the measure of a central angle helps us to know it's part of the whole of 360 degrees, its arc can also be measured in degrees. Thus, the measure of an arc is defined to be equal to the measure of its corresponding angle, central angle. So that's a big deal. We know that the central angle is equal to its intercepted arc. We're going to have two relationships, and this is one of them, and this is a big deal. So, example the circle above, what's the measure of SU? Well, it has to be 40 degrees because its central angle, right? Its central angle is equal to its intercepted arc, and SU is the intercepted arc. Now, it wants to know what is B is asking us, if we keep going, what's the major arc of SZU? Well, that should be pretty simple. There's 360 degrees in a circle. I've just spoken for 40 of them. So what's left must be 320 degrees. So again, that's the major arc. That's the measure of SZU. So the minor arc is 40 degrees. The major arc is 320 degrees. And hopefully we're okay with how we solve that. So when E measured the distance from Syene to Alexandria, he measured the length of an arc. This distance is called the arc length, and it is measured with units of length like centimeters or feet. One way to determine the arc length is to wrap a string about a part of a circle and then straighten it out and measure its length. However, if a figure is not drawn to scale or is too large to measure directly, then you must calculate the arc length using other information. So calculate the arc length of SU. So we know it's 40 degrees of the entire circle, right? We know that the radius is 12. So what we can do is we can say, all right, well, 2 times pi times r will give me the circumference of this entire circle, right? It has a radius of 12. And I just want to know how much this little chunk of it is. So I'll multiply it by 40 over 360. That's going to give us the length of SU. So I'll go here. I will grab this calculator. I will say 2 times pi times 12, because that's the radius, times the fraction of 40 over 360. And I like to do it the tops first, and then I'll divide it by 360. Is going to get us 8.37 or 8.38. So this is going to be 8.38 inches. That's how far this is, 8.38 inches. Which makes sense if the whole thing is going to be 24 pi, which would be what, about 72 inches? Then this little chunk of it would be 8 inches. All right, so 1063, inscribed angles. So in the diagram at right, angle BDC Angle BDC is an inscribed angle. We need to know what an inscribed angle is, so make sure you have that. Because it lies within triangle A, again, circle A, that's how we're going to name that, with the midpoint. And its vertex lies on the circle. So any of these would be an inscribed angle, where the vertex is on the outside of it. That's what we're looking for. Those are all examples of inscribed angles. So it corresponds to central angle BAC because they both intercept at BC. So you'll notice this central angle intercepts the same arc as this inscribed angle because they both hit BC. So they both have the same intercepted arc. So in the figure at right, angle F hits this intercepted arc. Angle G hits this intercepted arc, and angle H hits this intercepted arc. Well, it stands to reason that these all must be congruent angles because they all intercept the same arc. So if you were to grab a tracing paper or a protractor, you would see that these all have the same angle measure because they all intercept the same arc, which is important. Inscribed angles that intercept the same arc are equal to each other, but that's not the big second one that we want. So it says now we want to compare, and this is the relationship that we care about. Now compare the central angle to the inscribed angle. And what we're going to find is this, that they both intercept the same arc, right? So let's say that this is 50 degrees. Well, we know that this would have to be 50 degrees. We learned that up in this problem up in 1061, I believe, or 1062 we learned that. So what about this inscribed arc? Well, what it looks like and what you would find, and again, it asks you to sort of use tracing paper and test your idea or protractor or whatever, that this would equal 25 degrees. So the central angle, this is the first thing we learned, the first relationship is the central angle is equal to the inscribed arc. Well, the second thing that we're going to learn is that if you double the inscribed angle, oh wait, I keep calling it inscribed arc. It's an intercepted arc, my mistake. Intercepted arc. Okay, so if we double the inscribed angle, it's going to be equal to the intercepted arc. Or, to write it the other way, if you know the inscribed angle, it's going to be equal to half of the intercepted arc. It doesn't really matter. It's the same relationship. You might be twice as old as your brother, or your brother might be half as old as you. It's the same idea, right? So that's the same logic there. So what does all this mean? Well, let's tie this together in 1064, because at this point, if you're really confused, I apologize, and I definitely don't feel like this video came together in the way that I wanted. There's a lot of just sort of extraneous information at the beginning of it, but I think the problems are pretty cool. Plus, I think they're pretty rigorous, so I didn't want to just skip them over. But let's get to the payoff. The payoff is 1064. So really, this is the entire video in a nutshell. Real quickly, I don't know why I insist on doing this. Okay, there we go. So here's the entire video in a nutshell. Hey, look, I have an intercepted arc of 118 degrees. This must be half of it. This inscribed angle must be half of my intercepted arc. So x must equal 59 degrees. Because if I double 59, I get 118. So here, hey, look, this inscribed angle is 41 degrees. If I double it, I'll get my intercepted arc. So this must be 42. Then they get a little bit kind of tricky, which is kind of neat. So here, they want to know x's. Well, look, my inscribed angle is 90 degrees. Not only that, but look at my central angle. My central angle is 180 degrees, right? So either way, that would make this 180 degrees, either because the central angle is the same or because the inscribed angle can double to it. Next, I can double, now look at this inscribed angle. It intercepts this arc. So the relationship should be, if I go ahead and double the 78, I should get what y equals. So if I double 78, I get 156 degrees. Now, there's a couple ways I can get z. First of all, I know it's 360 degrees all the way around. And I've already spoken for 156 of it here and 180 of it here. And the only thing that's left is z. So if I grab my calculator and I say, all right, well, what's 360 minus 156 minus 180? What's left over should be z, which is 24 degrees. The other thing I can do is this. I can say, all right, well, let's ignore the arc and let's instead focus on this triangle. This is a right triangle. So I know that these two angles have to add up to 90 degrees, right? Because 90 plus 90 is 180. So this would be 12. And if this is 12, this inscribed angle is 12, then the intercepted arc is doubled and equals 24. So that's how we can solve for x, y, and z in this problem. Same thing here. It's kind of interesting on this one. I know that the central angle has to equal the intercepted arc, and I know that the inscribed angle is half of the intercepted arc. If I go here, I know that the central angle is equal to the intercepted arc. Now, the other thing is kind of what's going on here, which is kind of interesting. You can see this inscribed angle is half of this 114. So this must equal 57. And again, if you're not sure, what I'm saying is if you look here and here, this 114 is the intercepted arc of this inscribed angle. So kind of interesting. And finally, if we go here, well, this doubles to become 56, but then, hey, look, these have the same intercepted arc, right? This intercepted arc works for this inscribed angle, but it also works for this inscribed angle, which tells me that those inscribed angles must be the same. They both must equal 28. So again, I think the payoff of this video is this, this last problem. Make sure you understand the intercepted arc, the central angle, and the inscribed angle relationship.